students. Looks like we have some former students and some presenters.
So actually, I know where the students are in the back row. That's my own rule, and that is to sit near the door and have a fast car outside to pay for the lectures, not so interesting. Actually, I have a daughter who will be starting here in Stanford next fall. She applied in early admissions and made it. You know, Grace talked a lot about me, and it's truth. I know how to make great designs, and you make great designs by accumulating great people. There's no single person that can pull off all of these wonderful projects. It really takes a lot of people who are hardworking and talented and bring some special quality to bear on a project. And if I have a talent, it's maybe the kind of facilitator in getting people to think about different ways of approaching structural engineering and architecture. So, initially, Greg asked me if I would talk about the development of the structural engineering profession, and I agreed to do that. And then I just sort of ran out of steam. I have a lot on my plate, and so instead, I'm going to show you something about the World Trade Center. But just in case you think that's all we do, this is a project we're now doing in Shanghai. It will be the next tallest building in the world, 500 meters to here. And we're in fact, the fourth structural engineering project. And the trick is to take a project that was supposed to be this high and smaller in plan area and put it on foundations that are already constructed. So we put a new kind of structure inside it, which in concept looks something like this. There's a concrete services floor, and it's a brace system, and it's entirely column-free in this area. So the goal here, of course, is to make money for the developer. That's why people build buildings. They don't build buildings to make you feel good or we feel good. They build buildings to make money. So we try to make money for developers and contractors and other people. The World Trade Center, for us, started in 1962. The architect, Minoru Yamasaki, received a commission to design the project. We had been working with Yama largely because of the talents of one of the partners in the firm, Jack Christensen, who produced a fantastic design in our first venture with Yama. But we got this project not because of Jack or because of me, but because neither one of us could have done it, but because of John Skilling, who's one of these persons who has the golden tongue and a real entrepreneur type. And so he was the one who actually made the pitch, which got us the project. So what is there about the Trade Center that's unusual? It has what we call a tubular framing system. People say, well, who invented the tubular framing system? And frankly, I don't know. I always blame it on Yamasaki, and he always blamed it on me, and I always blamed it on Fazler Khan. So somebody did it, I'm sure. We call it an outrigger system. It was the first project put together for which has a linkage between the services core and the lateral core system, which in this case is in the outside wall, kind of giant space ring. And it was really neat because we had designed it but not actually included it in the contract. In structural engineering, it's good to have a back door. If this thing don't work, what are you going to do? So the space ring was part of our back door. And then a decision was made after all the steel was fabricated to put a 440-foot high tower on top of this building and another one perhaps later on top of that one. So the space ring, of course, solved that problem immediately. We did prefabrication of structural steel to an extent that has never been done before or since. We took a technology developed by two brilliant Danish engineers, Jensen and Frank, who had looked at wind loads on farm structures, on barns, in the full scale, and then they put replicas in the wind tunnel and tried to make them match, and they didn't. That is, in the wind tunnel, they got a downward push on the roof, and in the real building, they got an upward push. We all know that's the case. And so they came up with the idea we call a boundary layer wind tunnel, that is to create in the wind tunnel the turbulence of the natural environment. And then in order to decide how much the buildings could move, you have to understand that the World Trade Center was the first high-rise project in which anyone ever thought that it did in fact move. So we built, in fact, 2 different motion simulators to find out how people would respond to the kind of motion of a tall building. I interviewed a lot of psychologists, and they say, what are you worried about? People ride in cars and ships and planes. With building's just another kind of motion, they'll accommodate. Well, the World Trade Center is $1 billion project when it was constructed, so you don't invest $1 billion without being very sure. I went and rode motion simulators, and I have to tell you, if you ever get a chance to ride the motion simulators they use in the space industry, don't. And then, in order to deal with the structure motion, we came up with the idea of a damping system. We looked at lots of different kinds, but eventually chose a viscoelastic damping system. We developed a theory for taking the statistical nature of the dynamic pressures from the wind on the glass as opposed to the statistical nature of the strength of glass and put them together to try to determine the breakage rate of glass itself in the building. And in buildings at that time, all the walls inside the building were made of block masonry, and they leaked a lot, and they were very expensive to maintain. And so we developed again a theory for stack action. That's large buildings, kind of like a chimney. Cold air outside, the air rushes in at the bottom, rises up through the building, and goes out at the top. So we worked out a system that evaluated that so that we could design the support that we need for those pressures. And then it was, I think, probably the first and maybe the last high-rise building or craft outside of the military and the atomic energy industry, first designed to resist the impact of a jet aircraft. In this case, the 707 intercontinental version, which was the largest aircraft of its time. We thought it was lost in the fog headed toward JFK or elsewhere, similar to the Mitchell bomber that struck the Empire State Building. And we came up with a new kind of partition system that is airtight, allows for building motion, and completely changed the dynamics of a high-rise building, but is now the standard partition used in high-rise buildings around the world. And then we developed a technique for ordering and producing the shop drawings from digital format material to an extent that has not been equal since. And this is Yamasaki. Probably some of you read that he was afraid of heights, that he had these narrow windows. Yama was not afraid of anything. There was nothing on his planet that fazed him. I mean, he was maybe a little insecure with heights, but he's definitely not afraid of heights. So the structure has a 60-foot clear span on two sides and a 35-foot clear span on the other. And one thing to notice is that the columns in this direction are very long and hence very strong. They're box columns, very big box columns. And in this direction, there are lots more columns that you strike a line through, but they're, if you will, in a weak axis, so they're much less strong. This is the computer that we use, or a tiny piece of it. Now, this washing machine down here was one of the 5 disk drives that we had. Each one had like a long playing record, except it had 7, I think, records inside. This is called the IBM 1620. It was their first solid-state medium-scale computer. We called it Cadet, which meant can't add, didn't even try, because 4 plus 7 by looking it up in a table. So this is the site. It was the site of what was called the electronics industry. Electronics meant vacuum tube. So if you had a radio, it was a vacuum tube radio, and you went down here to get the real cheap stuff. And a lot of controversy over moving all these businesses out of that space. A lot of controversy. But they were well compensated for it, of course, but I don't think you can really ever get compensated by when you're upended. And this whole district disappeared out of New York. There was no replacement for it. So there was no place you could go. Instead, there was a store here and one over there and someplace else. Now, we surmised, we didn't know, but we surmised that in the wind, if the wind blows, say, in this direction, that the building would lean more or less downwind, not directly downwind, but more or less downwind, and then would oscillate about someplace. This was a This came from experience that I had in working on offshore structures. I knew that that was kind of what they did, and I thought, well, a high-rise building might just do the same thing. You have to understand the dynamics of high-rise buildings in the wind did not exist as a subject at that time. But this is a view of Lower Manhattan, and you can see that the wind coming from the south headed up towards the northwest goes over all these high-rise buildings. It becomes very turbulent, whereas the wind which is coming from this direction is over the water. It's very smooth. And so we designed for these two circumstances using this wonderful idea of Jensen and Frank. And here you see the wind tunnel model. And remember, this is a $1 billion project. So put a big tower on top of this building, the telephone company building, put an anemometer on it, another anemometer on top of this spire, and down on another tower on top of the New York Athletic Club. And we measured in the full scale the turbulence of the wind over the city. And then we replicated it in the wind tunnel. And sure enough, it replicated. So it gave us a lot of confidence that where we were going was kind of sensible. Remember, it's $1 billion. So, and I was 34 years old. So, so here you see an example. This was an anemometer which was on the telephone company building, now called the Verizon building. And you guys can see it, an anemometer on top of that spire. The shaft wall partition system was wonderful because it was designed specifically to allow the structure to move without restraining it, and allowed the structure to move and still stay airtight. And arrived at the idea because I rode on top of a lot of elevators in New York City, and well, I went through all the buildings I could. Remember, the tallest building I'd worked on was 22 stories, so I thought maybe people who'd worked in New York might know something more that I didn't know, which for sure they did. So I decided that partitions, the basic partition system, were terrible, and sat down and came up with this concept, which was then developed by U.S. Gypsum. We did a complete structural analysis of the Empire State Building. This is a trace taken off of from accelerometers, taken off of the building. You see it's very almost random. No kind of neat oscillation can be found there. The only way you can come up with a period of vibration is to drop all these data into a computer and analyze it, and it tells you that it's around 10 seconds, but you can't measure it out here. So, hey, that's a 10-second period building. No way. So, entirely different. And what was it about the building? The Empire State Building was designed for no wind load at all for the first 100 feet, and then 20 pounds a square foot above that. And we were designing the World Trade Center for something in excess of 100 pounds a square foot. So you'd think that the Empire State Building would have collapsed, or we were wrong. But we did a structural analysis of the Empire State Building frame, and we found that we could, of course, develop the stiffness of the frame, so we knew just how it would deflect under a given lateral load. And then by putting this kind of data from accelerometers and knowing the density, it's possible to experimentally determine the stiffness of the building. And we found that the difference was a factor of 5. That is, the building was 5 times stiffer than the steel frame. And all that came from the infill action of the masonry of the building, and we were designing a building without any masonry. The Trade Center trace looks something like this. You see it's a really neat oscillator. And then the motion simulators, all kinds. We built one which is a pendulum. This is the first one. Now, motion in a high-rise building is not a good subject, particularly since no one had ever worried about it before. So we went as far away from New York as possible in a little town in Oregon and built this simulator. And tested people who had no idea what was going on. It was very carefully disguised, so you went into the simulator without, you didn't see any of this junk. You walked from a very nice little office into the simulator. We tested people who had no idea what was going on, gave a little eye test, and then we would start the platform moving and wait to see what happens. We had other people who were told that it was a motion experiment. Some people we retested, we had tested months before. We had one man who was told nothing, and you have to understand, it's a little town in Oregon, and little buildings do not move in Little Towns of Oregon. They just don't do that. He was actually holding onto the walls. He would not respond to the fact that there was a problem. He was holding onto the walls, people falling over, because we could get this thing really moving. And then the dampers, very simple devices. They're about a meter long, 3 feet long, and made of viscoelastic material, which in itself is a long story. This is a load deflection diagram for a damper. As you probably all look through the structural field or electrical field would know, the area underneath this curve is the energy consumed in the device. And here you see one of them actually in the building. Am I speaking loudly enough? In the back? Yes. Okay. Thank you. And then a glass. This is the glass is very narrow and very tall. And here you see the deflected shape of the glass. In this case, it's deflecting about 4 inches. And there was no data available on glass of this aspect ratio, that is long and skinny. Those of you who are structural engineers know that the strength is not really related to the span, it's more related to the area of the glass. But anyway, we tested lots and lots of panes of glass to find out how strong it really was, and also to determine what kind of glass to use. And ultimately, it's a semi-tempered glass went into the project. And interesting enough, about half the breakage of the glass has been due to bullets. That is, people from far away, they get a rifle out and they lob bullets for fun, I guess. And at the lobby level, one guy was going by in a pickup truck, and he had a slingshot with 1-inch diameter steel balls, and he would shoot it at the glass, and each time he was successful in breaking one, it was $15,000. So here you see prefabrication. This is the bottom, this is the man, of course, the bottom of the piece, and this is the top. So these are big, big panels. These were prefabricated, and these were prefabricated, and the guys that go on top of that one. The floor system was prefabricated. Everything was prefabricated. Here you see in fabrication, now the length and width, the grade of steel, the welding that went into it, everything was provided to the contractor in a punch card format. Those of you who are very ancient like me know what a punch card is. It's about so big, it's got lots of funny little holes in it, and from that you can read data. I don't know when they stopped using them, but probably before you were born.
Still using it for loading.
Oh, I guess that's true. Yeah. Well, we still use FM tape recorders too, but you know, I don't know. Here you see some of those panels and coming to the site, ready to be erected up in the project. So it was an enormous logistics operation. So that panel we were talking about was spliced here. This was also prefabricated. When these aluminum panels were being put up, it was February, and the workers said, hey, you know, these things are split, they're cracked. Now, steel was pretty much topped out, and if you don't think having split connections at the bottom is not an interesting subject, it was, of course. So we pushed the panic button and decided that the problem came from water inside and freezing. And again, we went as far from New York as possible. Actually, we went to Berkeley, hired 2 esteemed professors who produced a report a month and a half that took them to do it that agreed that it was a freezing problem. In the meantime, we had to fix them all, of course, because you can't wait around for reports. This is sort of the standard piece. You see this bulge. Now, our client, the Port Authority of New York and New Jersey, was a fantastic client, absolutely incredible client. They never said no on any subject. Well, they could be a little tough sometimes. But this is one instance when they overrode our judgment, and that is they put the control of water inside of the structure in the hands of the contractor. And our policy is steel plates on all box sections so that you cannot get water inside for this very reason. Indeed, that night, some 85 pipe columns broke on the split on the adjacent small buildings that are under construction. These box columns were used for everything. If you had a hose, and water running out of it, you didn't put it down. You just put it in the box column because then, you know, it didn't get people wet below. So there was water everywhere. We took out of some of these columns 600 gallons of water. And then, you billion-dollar project, let's not forget. After it was all done, got a completely new team, went down, looked for water, and found it. So, very big problem with water inside of college structures. But anyway, we've got rid of all of it. It's a prefabricated wall panel. There were thousands of these manufactured. And the steel, all the steel plate came from Japan, so punch cards. No way to send them across except by airplane. Today we wouldn't bother, but so this plate and this plate and so forth, all of these were fabricated in Japan. In the United States, the steel industry was in the mood of, well, this is what we make, how can you use it? In Japan, there were, what is it that we could make that you could use? And so we bought steel for the project in increments of 5 psi, which is fantastic, of course, for the overall toughness of the building, really fantastic. So we didn't have over-yield material in the project. These were fabricated in the state of Washington. And this is a readout of punch cards. Now, Port Authority Legal Department said, okay, well, this is the basis of the contract. And we said, no, it's got to be the punch card. No, they said it had to be this one. And of course, the legal department won. But ultimately they did. The contractors came back and said, hey, we saved all this data and we want it in the punch cards, and then we don't want to use these at all. We just want to have the cards. That should be the basis of the contract. And ultimately, they relented. The legal department relented. They were assembled something like this, a spandrel plate, a big broad plate, and the interface of the column plate was welded together, butt welded together. And then this shown in blue, another assembly with the stiffener plate inside was then added to it, and the outside wet plate was added last. Notice that there's no weld between the stiffener and the outside wet plate. Today, it'd be just like that. I mean, you pop this into your favorite finite element program, and out would come an answer. But at that time, that technology was not available, and so we did most of the finite element work based on very big programs, but not suitable for actual practical work. So we did a lot of finite element work on the World Trade Center. This kind of example also is the physical testing, of course. So the way it was put together, like this: first the bed sheet as well as the flat plate, then the stiffener and the flange plate, and finally the wet plate on top. And it was done with such precision that it was possible to maintain a very tight tolerance between the architectural work and the structural work. And normally we would allow in here about 2 inches, that is 4 inches at the very least. But since our columns were 14 inches, that 4 inches was a big number. Here you see the fabrication. This is that sort of bed sheet, fabricated first. It was, in my experience, the first time that steel fabrication was done with the material moving by the workman rather than a workman going to the steelwork, i.e. Leaning back on the technology, I guess, first popularized by Henry Ford. Then assembled into big panels. Then these went into a jig, and the ends of the 3 columns were all milled in the jig without moving it. All the bolt holes were drilled in the panel, again without moving it. So we were able to maintain very, very tight tolerance of these panels. And it went together sort of like a Lego set. It was fantastic. They just went up, no problem. Put them together, there were 2 holes, a large hole above at the bottom of the column and a smaller one at the top of the column. Basically put the impact wrench for tensioning the bolts right inside the column and tension the bolts. Floor system was prefabricated. In this case, this panel 60 feet long, 20 feet wide. Metal deck was already in place. Electrical distribution cells already in place. So when you put one down, you created quite a significant space, 1,200 square feet. Here you see a panel in the air. There was one attempt to bring these over by helicopter. These, of course, weigh almost nothing. They're just mostly air. And the pilot got over New York Harbor and decided that he wasn't going to risk his life to carry it any farther. So sometime if you're out scuba diving in New York Harbor, you'll find the subsea architect center. So they asked that we maintain big openings. So this a large opening, and then diagonally across the building, oops, this way, sorry, there's another opening just like it. And then go down the side, you have this one. So the openings are diagonally opposite each other like this, so that at no one level do they cross the complete building. But they were never used. Great idea, like a lot of great ideas, didn't find fruition. So here you see there's something about the whole assembly. The prefabricated wall panel, prefabricated floor panels, and so forth. Not shown as a damper because they were put in later. The floor system, been a lot of stress about the floor system being very vulnerable to all sorts of things. But in fact, it was designed so that you could remove, depending upon where you were, 2, 3, 4, 5, sometimes 8 of these trusses, and the whole system remained stable. With a grillage, as you can see here, a grillage of trusses, not just a one-way system. Very, very sturdy system. And a lot of talk about the connection of these trusses to the outside wall. The normal criteria used by structural engineers is that the connection to keep a column from falling off the building, if you will, is you use 2% of the axial load in the column. That's a good rule of thumb. So this is 2%. And this shows the actual connection capacity that was built into those spaces. So if you take the North Tower, it was designed for something like 15 or 18 times more than what you would consider standard criteria. Here you see something about an important aspect of the Trade Center, and that is not a single ironworker lost his life on the project. And that in no small measure because of this jail-like exterior of the building. Notice that the panels are spliced, only 1/3 of them in any given level. As this is a splice, up one floor, another one, up one floor, another. So that there were no column splices in 2/3 of the columns in any given level, which again provided for toughness and redundancy in the structural design.